So today we kind of, in some way, end our journey of about exploring the trade-offs between attribute similarity and locational similarity. So we started with a very simple approach, the spatial autocorrelation measures that summarize attribute similarity in some scalar measure, cross product, square difference, and then summarize the locational similarity in a spatial weights element. And then we explore that both from a global perspective as well as a local perspective, where we actually started to identify clusters as specific locations of interest, let's just put it that way. And then we moved into more of a different concept of clustering, namely a concept of grouping of observations. And we started with the classical approach where we grouped observations only considering the attributes. So we don't worry about location at that point. We just look at the attributes. We looked at the problem of the curse of dimensionality, reducing dimensions by means of principal components, or visualizing similarity by means of multidimensional scaling, and then the classics, k-means, hierarchical clustering. Today, we throw in space. And so we move from just clustering based on the attributes to including a consideration of locational similarity, in the sense that whatever cluster we come up with has to consist of elements that are contiguous, that border each other. And there's different ways, as we'll see, in which we can approach this. I'll start with some generic notions, then I'll give some ad hoc solutions, which are actually sometimes work amazingly well, but they're not clean solutions. And then I'll go over in some detail two algorithms that have, two heuristics, I should say, that have been proposed to address this issue. So an algorithm, as you probably know, is a series of steps, of computational steps to accomplish a solution. A heuristic is an algorithm that cannot be proven to give you the optimal solution, but gives you reasonably good solutions. So that is going to be something we're going to keep running into. These spatial problems are what we call NP-hard, which means they're combinatorial. They cannot be solved by enumeration except for toy problems. So you never know whether your solution is actually the best solution. All we can do is guarantee, and there's proofs of this that I won't do, that the solution is a good one, but not that it is the best one. So keep in mind, even though in GeoDa now you can do this as point and click, this is really not a point and click frame of mind. It's very much a frame of mind where once you find a solution, change some of the parameters, try it again, and see if the solution is stable. If you always end up with the same thing, you can be pretty confident, but you can never prove it. You never know for sure that you're not stuck in some local. And there are many, these are really, really hard problems. And to do this at a industrial scale level is really tricky. And a lot of these algorithms at first sight, you know, seem pretty reasonable. But then if you implement them at, you know, production grade scale, it doesn't work. It takes too long. So then you have to resort to parallelization, throw a lot of hardware at it, or rethink the algorithms and things like that, which I'll get into. But it's still a very active and, to me, fascinating area of research. So what you have in GeoDa and also in R will be good enough for, you know, a couple of hundred observations. Once you get into the thousands, it will either take a very, very long time to converge, or it won't converge at all. It'll just blow up. So this is something to keep in mind. You know, don't throw 10,000 observations at this. It's not going to work. And I'll try to explain why it's not going to work. So the problem, which we've now seen a couple of times, is we're going to group observations in similar entities, which we call clusters, but these objects have to be contiguous. So they have to border each other in some geographical sense. If you remember the k-means and the hierarchical clusters that we obtained last week, if you looked at the cluster maps, they were by no means contiguous. They were all over the place. Right? Some were a little bit contiguous, but most of them were not at all. So here we address, again, head-on, this tension between attribute similarity, which is similar in attribute space. So to make this concrete, if you can, think of our 3D data cube that we saw in the exploration part. So we had the 3D scatter plot. So you had a cloud plot of points in 3 dimensions. So points that are close together in these 3 dimensions, or alternatively, in our parallel coordinate plots, lines that clearly followed each other form what we called clusters. They are similar in attribute space. Now what we want to do is add an additional constraint to that, in that it's not enough that they are similar, that they're close in this 3D cloud plot. They also have to be close geographically. And so that is a tension in the sense that you can't have it both ways. In that the best solution in terms of attribute similarity will typically not satisfy your locational constraint. And the best solution in geographic terms will typically not satisfy your attribute similarity constraint. So you cannot have it both ways. These are typically 2 objectives that are fighting. So every solution consists of finding some compromise between the 2. And compromise in the sense that we will try to get the highest possible attribute similarity while still satisfying our contiguity constraint. Because that contiguity constraint is what makes this different from just regular clustering. And the terminology about this is a very old problem. Has been around for a long time with different solutions, and it's known in various literatures under different names. So you may be familiar with a particular flavor of this, which is redistricting. So redistricting is a political process where electoral districts are literally delineated based typically on a criterion of equal population. So 1 person, 1 vote. Each district is supposed to have the same size. There's all kinds of complications to this. There's a huge literature to this. But in essence, it's a spatial optimization problem of this flavor, spatially constrained clustering. So it's known as spatially constrained clustering, as contiguity constrained clustering, clustering under connectivity constraints, lots of different terms, but it's all the same thing. You have these 2 objectives that in a sense are fighting, the attribute similarity and the geographical similarity, or the contiguity. So in classic clustering, we have, as we've seen now a couple of times, these 2 possible metrics. One looks at within group similarity. So we look at each cluster and look how similar the elements in that cluster are, and we call that the within group sum of squares, and we want that to be over all the groups to be as low as possible. So the greatest within group similarity that we can obtain. Or equivalently, because the total variance, if you wish, or the total dissimilarity is the sum of the within group and the between group. So there's really 4 different ways in which you can formulate this, but they're all the same. Right? You can maximize within group similarity. You can minimize within group dissimilarity. You can maximize between group dissimilarity, or you can minimize similarity. So that's 4 ways to express this, and they're all the same. If you see this in the literature, depending on the particular take in a particular optimization approach, one or the other of these 4 formulations will be picked. But it's important to remember they're all the same. They're all measuring either one thing or its complement in 4 different ways. So we have that, which we know how to do, more or less. And then we throw in the contiguity. And the contiguity, as we've seen, is or can be defined by a spatial weights matrix. And then in addition, although I'm not going to really talk about that too much, we can throw another one in there, which is the shape of the clusters that we obtain. And this is actually very important within the redistricting discussion, is whether these resulting groupings are compact or not. Because contiguity and compactness is not the same thing. Think of a string of areas that are just kind of strung along and each has one or two neighbors on each side. So it's kind of a snaky string, which is perfectly fine in terms of contiguity, but of course that's not compact at all. In fact, in the literature this is typically called gerrymandering, but you know, as a pure spatially constrained problem, solution to a problem, it's fine, but it's not compact. So we can throw in compactness in addition. We won't do that explicitly here, but I will show you how some of these algorithms favor compactness more than others. So in the literature, there's this review article that looks at many different approaches. I'll just take a subset of this, but essentially there are methods that approach this without explicitly taking into account contiguity. So they get at this kind of through the back door indirectly, and they start with either a conventional solution like a k-means solution and then fiddle with it, or they try to trick the attribute similarity to obtain compact clusters. Typically, as we'll see in a few minutes, this is done by including the coordinates, xy coordinates of the units as part of the attributes that are to be maximized. And then the other branch takes the contiguity into account explicitly, and there we have basically different flavors of spatial optimization, where we have, these are all kind of, if you wish, examples of location allocation problems. So a location allocation problem is where you have to choose a number of locations, say warehouses, and then you assign a district to each of these warehouses in such a way that the whole area is used up. So you can think of this, our clusters. Cluster centers are the warehouses, and the clusters themselves are the market areas or the service areas that are serviced by these warehouses. Mathematically, these are all the same. There's a huge literature in operations research on location allocation problems in its different flavors with different objectives, functions, different kinds of constraints. So these spatially constrained clustering methods are really special flavors of that more generic problem. So just briefly a review, and then I'll go into some of these in more detail. So classic clustering with updates. We start with a classic solution, either hierarchical or k-means, and then we either combine units so that we end up with contiguous clusters, or we split them. And I'll show you in a few minutes what that looks like. Bottom line is very inefficient, and you really don't know what you're going to end up with in terms of solution. So that's a very old, suggestion. Then, still old, but not quite that old, is to introduce xy coordinates into the optimization problem. So the rationale is, if you add the centroids of the observations as part of the attributes that you try to make as similar as possible, that will tend to pull the clusters towards their overall centers and make them more compact. Do they make them compact enough? That is a problem specific. And another way to deal with this is to turn it into an explicit multi-objective problem. Multi-objective is having multiple objectives. So one objective is attribute similarity. The other objective is locational similarity, and so we do some kind of weighted optimization. Then the question is, what should the weights be? Right. So then other approaches are heuristics, and one has been around for a while. It's called AZP, Automatic Zoning Procedure, and it's basically trial and error. So you start with an initial solution that is feasible. So let's say you take a k-means till all the clusters are contiguous, and then you start swapping. And basically what these algorithms do is they take a candidate, see if the objective would be better if it was moved from cluster A to cluster B. Keep doing this in some kind of organized fashion until you find a solution. The problem with this, as I mentioned, it's a really hard problem. It's what in OR we call an NP hard problem. Whenever you see that NP hard, walk away because there's no solution, right? And, you know, it's a heuristic, so you don't know where you end up. You can easily get trapped in local maxima. And it's still an interesting thing to do, to learn about, you know, the structure of the data. All these things are really interesting to do, especially with smallish data sets. And that's why I'm using the French data set. Because, I mean, hopefully you get a little bit of intuition about how this actually works and what's going on behind the scenes. And with the French data set, you can actually kind of see it. If you do all the US counties, you can't see it. There's just too much going on. So then there's another branch, if you wish. I mean, there's no pun intended, which Skater is an example of, where you represent the contiguity structure as a graph. And we've seen this when we talked about spatial weights. In one of the exercises, you create a neighbor list in R, for example, and then you can represent it as a graph structure where each observation is a node and there are edges between the nodes that are neighbors. And it's as simple as that. And so then the idea is, with this graph as a starting point, we're going to cut it in pieces, and each of these pieces will be a cluster, which by construction, because you take into account the neighbor graph, will be contiguous. And Skater is an example of this. And then the most difficult approach, but also the most, in some sense, theoretically satisfying, is to formulate this as an explicit optimization problem. And specifically, this is an example of integer programming. It's called integer programming because the decision variable, the variable that you used in your objective function, is a 0, 1 variable. So is observation I part of cluster K? It is or it isn't, 1 or 0, right? So then you try to find a solution of the optimal allocation of the 1s and the 0s that maximizes your objective. And so this is a branch of operations research. The typical kind of algorithmic approach is called branch and bound. You may have heard of that. But I won't get into that. I will just show you what these things look like and how, in some sense, what kind of contortions you have to go through to formulate this as an integer programming. And the problem with these integer programming approaches is it's always the same thing. How do you deal with the geography? How do you deal with the contiguity constraints? And that typically ends up being a graph presentation, but not necessarily, not uniquely. And as I said before, there are several ways to do this. There's actually quite a large literature. So let's get a little concrete, and at first I want to show you some indirect solutions. So first way, classic clustering with updates. And this is kind of fun. I actually had fun doing this because I did better than Skater with my eyeball method, which I will illustrate in a second. So there's basically two ways of doing this. One is you start with a given K, say K4. You do your clustering, and then you say anything that's not contiguous becomes a new cluster. So, well, I'll show you an example in a second. So basically what that does is K is no longer K. It becomes larger. So for example, in the illustration I'll give you, we go from K4 to K12 by just making everything its own cluster. That's a very naive approach. It doesn't really solve the problem because it doesn't really address the trade-off between attribute similarity and location similarity. It basically gives up. It says, okay, I'll keep what I have. I'll just call them a cluster and go home. The other one is what I call the eyeball method, is where you actually, by eye, or you can do it a little more sophisticated than that too, start swapping. And that's really what in the spirit of AZP, automatic zoning process. So you look at the clusters, And you see where maybe the simplest ways are to break the lack of contiguity. So like if you have two clusters with a different one in between, you make that different one part of the cluster, and so now you have contiguity. And you do this by making a small number of swaps. Obviously, the solutions are indeterminate. You can have multiple outcomes. The advantage is that you keep k the same. So if you want to see how the quality of the cluster changes with k, you keep the same k. In the other approach, k changes. Okay, so let's start with our 6 variables. They're always the same 6. And on the left is the k-mean solution with k equal 4. So we have 4 groupings. The size of the clusters is 36, 20, 18, and 11. And, you know, they're somewhat grouped, but not totally, right? So we have this big chunk in cluster 1, the light blue one, but then we have 3 other pieces besides the big chunk in the north. Cluster 4 also has 4 different pieces. Cluster 2 has 3 different pieces, and cluster 3 has 2 different pieces. So then if we make each piece that is kind of unconnected its own cluster, we end up with 12 clusters, including several singletons. A singleton is a cluster. It's not really a cluster. It's just a single observation, right? So that's, you know, you end up with contiguous clusters, but they're not that useful. So then the next approach is what I call the eyeball method, where you basically identify places where you can. If you look at the map on the left, in north, to dark green cluster. And you can do the same with exchanges. You end up with this setup, which is spatially contiguous. It keeps the k to 4, and then you can see how bad you're doing. So the ratio on the right is the one to look at. That's the ratio total between sum of squares to total sum of squares. So we want to maximize between cluster dissimilarity, which is the numerator, and then the total stays the same. So the higher the number, the better you're doing in terms of clustering. So obviously the best, quote unquote, is for 12, but that's cheating. We're not keeping the same number. You know, it's same as with principal components. If you do more of these, you will get a better score. The question is, how much better is it than the previous case? So we'll see in a few minutes. It's similar to the scree plot, where we look at where is it not worth getting another cluster in here. But then the contiguous cluster, by imposing the constraint of contiguity, we lose something in terms of attribute similarity. So that's the most important concept. There is this trade-off going on. You can't have it both ways. So if you want contiguity, you're going to lose a little bit in terms of your objective function attribute scale. So that's one indirect method. A second one, and I forgot to put this in my slides, but it's in the lab notes. Second one is also kind of cheating in a sense. Include x and y as attributes in the clustering algorithm. Now, the clustering algorithm know that these are x and y. It just treats any other variable, standardizes the mean 0, variance 1, just throws them in with all the other ones in the standard k-means or hierarchical routine. So what does this do? Because x and y are in there, and we're minimizing dissimilarity in the distances between x and y, we're trying to pull these units closer together. So ideally, we pull them enough so that they each become compact and contiguous. In practice, That doesn't always work. In our example, it does not. It does a little bit. Larger groupings that tend to be more compact, but we still have, you know, floaters, individuals that are not connected to the rest of the cluster. So that's a very, you know, easy method. It's actually kind of amusing to me when you talk about this with non-spatial machine learners. This is their favorite solution to the problem. Just throw in x and y, and it'll be fine. Well, no, it's not. It's not enough. It pulls a little bit, but you don't know how much you need to pull to get it to be contiguous. And so that's what we're going to do here. Now we make it an explicit multi-objective optimization problem. And I'll use this opportunity to illustrate an optimization strategy, which is a bisection search, which is a very straightforward but also highly effective optimization strategy when you have a single parameter to optimize on. And so we have two objectives, same two, attribute similarity and geometric similarity, which we operationalize as the square difference between the centroids. So we're trying to get these entities to be as close geographically as possible, which we get by minimizing the distance between the centroids. That's how it works. And so it's multi-objectives. You can't have it, you know, if you give full weight to attribute similarity, we're back with k-means. If you get full weight to geographic similarity, we basically do k-means on the x and y coordinates. And we'll see in a second what that looks like. They're two weights, but they're really not two weights. There's only one weight because they add up to 1. So if you have one, you know what the other one is. So we can couch this as a one-parameter optimization problem where the parameter is the relative weight given to one or the other. It doesn't really matter which one you pick because you know the other one is the complement. And then one way in which we can approach this is so for each particular layout, we get a value of the objective function, the ratio of between sum of squares to total sum of squares. And we want to have that as high as possible. And obviously, if we do k-means, which is, let's say, the weight for the distance is 0, we get the k-means solution. And if we do weight 1, then we get just a centroid solution. Right? And so these, in some sense, are extremes. The optimal solution in the sense that it satisfies contiguity and gets the best possible value for your objective function is somewhere in between. And that is an ideal setup for a bisection search. The rationale behind a bisection search, I mean, I can throw some equations on there and do some partial derivatives and stuff like that. But basically, the rationale is very simple. Since you have a bound on the parameter space, 0 to 1, you know it's in there somewhere, right? So if you had a lot of time and a lot of computing power, you could try out every possible value between 0 and 1 and just see how the objective changes. Now, to do it a little faster, we'll keep cutting the interval in half. You know, there's actually a slightly optimized golden search method, which is a little bit better, but it doesn't really matter here. This is just to illustrate the principle. So we have 0 to 1. We take the midpoint is 1/2. So 1/2 weight to attribute similarity objective and 1/2 weight to the distance, if you wish, objective, the geometric objective, right? And then we can see, this is why this is not realistic, it's a toy problem. So we could look at the map and we say, is this contiguous or not, right? If it is contiguous, that means we can do better in terms of the attribute similarity. And so if you think of this as moving to the right or to the moving towards 0, 1, we can move more, get a better solution in terms of our objective function, but we don't know if that is contiguous. So we take the midpoint between 0 and 0.5, which is 0.25. We do the solution, and we check whether it's contiguous. If it is contiguous, then we can move further towards 0. If it's not contiguous, then we take the midpoint between 0.25 and 0.5 and do it again. So we keep moving to the left or to the right, depending on whether the contiguity constraint is satisfied or not. And we keep taking the midpoint until the objective function doesn't change based on some criterion that we choose. You know, if it doesn't change, we say good enough, we stop. Now, I have to, you know, stress that this is just the way you can think about this, right? You can't actually operationalize for a large data set, but for this data set, you can, because you can look at it, is this meet the contiguity criterion or not, and then I think it's kind of a neat way to illustrate this one parameter optimization problem. Even though it's very simple and it's very old, it's incredibly powerful. And it also guarantees you can't get stuck in never-ending loops. You always stop somewhere, because you say it doesn't change. You know, I want it to stop when it changes at the 4th decimal. You will stop. You know. Okay, let's illustrate this. So we have the two extremes. At the top, again, is the k-mean solution, which we've now seen several times. And at the bottom is also a k-mean solution, but k-means based on y. And so we get very neat, compact regions into 4 nicely organized, compact solutions. This is about as compact as you can get it, right? So this is the extreme spatial solution where you ignore the attributes. But of course, you can figure out what the within similarity and the between similarity is for the attributes. You then use the attributes in the optimization, you can still see how well you do. And of course, the upshot is we don't do that well, right? This is about half of what we get in the k-means. I mean, a little more than half, but still considerably worse. So we give up a lot by just focusing on the geography only and ignoring the attribute similarity. So now we give each half of the weight, and that's the one on the top. So we do from 0.24, we go to 0.35 roughly, and it's contiguous. So the thing is the original 4 in different directions because of the attribute similarity. The attribute similarity weighs in and pulls them in different directions. And in our rationale, in our heuristic, we see, and literally that's what we're doing, we're looking at this and say, okay, this is contiguous. We can do better. In other words, we can give a higher weight to attribute similarity or a lower weight to the centroid. So we go to the midpoint between 0.5 and 0, 0.25, but we've overshot it. So we got these little ones here, and these are really hard to get rid of, actually, as it turns out. And then this splits in 4. So, but this one is contiguous, and so number 2 is contiguous, and number 3 is contiguous, but the other ones are not. So we overshot it. So now we have to go back towards 0.5. We take the midpoint, 0.375. We keep doing better on our criterion, but here we still have this one that we can't get rid of. So then we have to move closer to the contiguity criterion. So we're going to do a little bit worse on the total objective function. This goes down a little bit. But if you keep doing this for a while, you stop at 0.45. And that's contiguous as well as you can do on the objective procedure to get you a solution that satisfies the contiguity constraint and to the highest attribute similarity given that constraint. So if we compare to eyeball method, I'm actually beating it, which gives you a sense of how complex this problem is. So you might think that this, because it's mathematical, will always be better. Not necessarily, because if you look, I'll be with you in a second. If you look at this solution, it's very stringy. So if you throw in the compactness, this is very compact. This is not. But when you give up compactness, you actually do a little bit better. With the definition of well, this is what I mean by the tension between the two, right? So if you don't care about the geographic part of it, then of course you don't need this. But the whole point is, in a lot of real optimization problems, the physical contiguity matters. For example, in the redistricting, it's an absolute requirement. In a lot of marketing applications, it's an absolute requirement. So if you don't need to satisfy that requirement, of course, then it's a different problem. But if you do need to satisfy that requirement, then there is a tension between how you define it. So Y solution immediately defines as compact as possible, and then Y part of this, you know, it's ad hoc, right? It's not built in. Scalar and max speed that we'll see in a few minutes, where it is actually part of the constraint structure, right? Here, you don't care about compactness. You just want to make sure that they connect, so you get these long, stringy. It's kind of the indirect way of approaching this. It works. It gets you solutions, but it's not totally satisfactory, in some sense, because it's predictable. So then the next approaches are examples of heuristics. They're reasonable. We cannot prove that they actually give us the best solution, but they give us good solutions. So scalar, don't ask me why the K is in there, but it's that's the title of the paper, Spatial Cluster Analysis by Tree Edge Removal, with cluster written with a K. And it's really based on a graph theoretical approach towards the problem, which is what a lot of the heuristics are based on. So the particular angle of this approach, and its appeal, I should say, is that it simplifies the problem greatly. So rather than dealing with all the possible solutions, it, in a constructs a constrained solution space. So the solution space is the set of all possible solutions, right? So if you think about this in kind of a intuitive way, you have a solution space that has 20 million possibilities. So in principle, you had to check every one of these 20 million to see which one is the best one, right? Whereas if you, in some reasonable way, not just arbitrary, but in some reasonable way, you can reduce this to, say, 10,000. Then you greatly simplify the problem and actually make the solution feasible. A constrained solution space, which in some sense might eliminate possible solutions that are actually better, right? That's always the trade-off. So the key concept here is that the initial connectedness structure, which is reflected in the spatial weights, is reduced to a simplified one, which is called a minimum spanning tree. So to give you a sense of what that simplification entails, if you think of a spatial weights matrix and we have, say, n observations, and say on average we have k neighbors. So we have a weights matrix with n times k squared, roughly, non-zero elements, right? And so those are all the non-zero elements we have to think about in terms of grouping entities. Now the minimum spanning tree has n minus 1 edges. So we go from nk squared to n minus 1, which is a huge simplification of the problem and which makes it tractable. So the idea is we have this weights matrix, we simplify it into a minimum spanning tree, and then we're going to cut the tree, literally cutting the tree, into subtrees, and each of these subtrees will be a cluster. Why will it be a spatially constrained cluster? Because the tree respects contiguity. It's built from the contiguity structure for the observations. So you get the connectedness automatically. You don't have to worry about it, because any solution you get has to be spatially contiguous by construction. Okay, so let me go through this step by step. So we start by, just as we've seen before, a generalized weight structure. Every pair of observations, ij, we have a distance measure between I and j, which is, for example, the Euclidean distance, but it doesn't have to be. It could be based on absolute differences as well. And as usual, the objective is to minimize within group dissimilarity, maximize between group similarity. These are the four things that I mentioned before. So it's always the same thing. Find of dissimilarity. Now there's that. And this is really the classic one, if you wish, is a Euclidean distance, but in some applications, absolute differences are better. Sometimes you can take correlation measures. If you have rank-ordered variables, you can do Kendall, Spearman type rank correlation measures. So as long as there's some formal expression of the dissimilarity between entities. In fact, this has been, in the machine learning literature, this is extended even to categorical dissimilarities and so on. So the essence is you have to have this distance matrix. And then, in addition, we have the geography. We have the contiguity. So this is for the French departments, the network, the graph that shows for each location, each node in the network is a dot. And then the blue lines are the edges in the network. Formally, that's what it's called. And they connect two dots that are contiguous, spatially contiguous. So this is the weight structure. So what we're going to do with this is load it with dissimilarity measures. So any one of these edges will get a value. So if you think of this, maybe you're familiar with transportation type problems where you want to find the shortest path through a network. So the same thing, the network has nodes, it has edges. Each of these edges has a cost, say travel time. So how you get from A to B, Google Maps, in the shortest possible time. It does a Dijkstra algorithm. It gives you the route on the map, and it tells you it's going to take you 25 minutes, right? Because it adds up the times for each of the segments and finds the shortest one. So we'll do something very similar. Travel times, the cost to go from B is this dissimilarity measure. So we have our dissimilarity measures, and we load them up on the edges. And then we can, for example, find the shortest path between an observation here and an observation there that minimizes the sum of the dissimilarities. Sound familiar? That's the same objective we've been doing all along. So then there's a special type of path in a tree, which is called a minimum spanning tree. And so a path in a tree is a sequence of edges between nodes. So you go from here to there, you go this way, then that way, then that way, then that way. That's a path. And so a minimum spanning tree is a very special path. It's a path through all the nodes that visits each node only once. So it's a real simplification of this very complex nk squared kind of order set of connectivity into n minus 1. So each node is visited once. The total number of edges is the number of nodes less 1. Cycle back. So we start at A, we end up at B, and we have this path through the whole thing that visits each node. So you may have had to do this as puzzles for or something like that. That's the kind of thing they make you think about, but it's mathematically is very simple. So formally, we have a graph. A graph is basically a collection of vertices or nodes and edges or links. A path is just a sequence of edges, V1 to V2, V2 to V3, and so on. A spanning tree is any tree that has this unique path, but then the minimum spanning tree is where we throw in a cost function, and in this case the cost function has to do with the dissimilarities. So how do we get one of these minimum spanning trees? There's a bunch of different algorithms, but let's just illustrate one so you get a sense of how this works. So there's one particular algorithm, I believe it's called PRIM, P-R-I-M. Different distributions of the cost. Now, the one thing to keep in mind, but this doesn't tend to be a problem, is that this solution is not unique if you have a lot of ties in the dissimilarity measures. So if the dissimilarity measures are unique, you can show there's a unique solution. But if they're not, then the solution is not unique. So then you can set up. We start with any one point, and in this particular example, we start at the lower right part, and we look at this, and we take the one with the smallest cost. And that is our first link. So we go up in this graph, it's called LA. Then we look at all the nodes that are part of this, so we have 2, and all the possible links, and take the one with the smallest cost. And that's the second edge. And so in this case, we go up to LB. And then we repeat. For each of the 3 nodes now, we look at all the possible links and take the one with the smallest cost. So we keep building this tree, and after a couple of iterations, this is what we end up with. So each node is visited once. If you count the number of edges, it's less than the number of nodes. And this is the minimum spanning tree. So then the object will be, where do we cut this? So we'll try to cut this to optimize our objective. And so for the French example, take some time to learn, because it will explain a lot of maps that we'll see. If you do this too quickly, you don't think about it, and you don't, well, maybe, but I think it's hard to see. But see, there is already a structure in that all these southern departments are connected together. And see, 6 up there, or 67, connects through these guys up here and then goes north. And these guys come down and then go north. So if you cut over there, you actually cut the south north. And by construction, based initially on the connectivity structure, these are all contiguous. Okay? So that's what we start with. We have this minimum spanning tree. For each of the edges, we have the dissimilarity measure. And now we're going to cut. So where do we do the first cut? And to put it simply, we cut where it's best to cut. So this is not actually how it's done, but you can think of, you thinking of all the possible cuts that you could make in the tree. And of course, it's limited because it's a minimum spanning tree. So there's only n minus 1 if n is the number of observations. So in our French example, there are 85 observations. There are 84 possible cuts that we could make. And you could think of, for each of these 84, let's compute how the total dissimilarity decreases, or one of the 4 ways of putting it. But basically, we get better in terms of either internal similarity or between dissimilarity, which cut gives us the best result. And that's where we cut. So then we have two subtrees that cut the area into two, and we repeat the process. So in each of these subtrees, we find the cut that gives us the best improvement in our objective function. And so we keep cutting until we reach the number of clusters, k, which is preset, just like in k-means. So that's the idea. Now, think of what this does. So if we were, I wish I had a pointer, if we were to cut this tree somewhere, then the next cut has to be in one of the subtrees. So you can't swap. This is very different with what, say, AZP does, or as we'll see later, MaxP does, is where you keep swapping possible locations from one cluster to another. That's okay, thanks. Once we cut, you have two subtrees, and you cannot move an entity from one of the subtrees to the other subtree. You're kind of stuck. And so this is, in essence, a hierarchical top. You have two subtrees, then each of these gets further subtrees and further, but you can never jump back to a branch or another subtree. And we'll see that in the illustration in a second. So we do this, and this illustrates the process. So schematically, we'll look at all the different edges. The one there on the right is the best one. It disappears. So then we repeat the process. We find another one. We want K3. We're done. So each of these, by construction, will be contiguous because it's built from the connectivity, the initial connectivity structure, and it also maximizes our objective. So in the French case, as I warned you, it's very easy to cut there. We have all the southern have it here. You would have all, and then and on the map it looks like this. And of course we can compute how we do on the criterion. And then if we go to 6, what's going to happen? Well, to go from 4 to 6, one of these bigger ones is going to have to split. One of the other ones is going to have to split into. So the next higher k will always be nested within the lower k. So you start with 4, we go to 6, and you see that basically this one gets split in 2 and the middle one gets split in 2. And so it goes on. That's the nature of the scatter algorithm. So it's a very clever way to deal with it, but it's a simplified solution space, which may or may not give you the best, the optimal value. So it constrains the solution space, could get you stuck in local optima, and also it's kind of slow, because in essence you have to evaluate n-1 possibilities and then a subset of that. So that could be slow. There's ways to speed it up, but it could be slow. But it works. It gives you a very nice regionalization. Tends to be nice and compact regions. MaxP is a whole different game. So the problem, a problem in this clustering world is what is K? And I alluded to this a couple of times already. There's really no good way to pick K. And typically what one does is the counterpart, really equivalence of a scree plot, which we used that concept in principal components. So you plot this ratio, that is our objective, for different values of K. And then hopefully there is some point where you say, well, beyond this, it really doesn't pay anymore to do another cluster. We don't really gain that much. Unfortunately, and we already sort of know this data set is kind of a pain when it comes to this. And so there's no, at least I don't see it, no clear elbow here, no clear kink in this process. So max P, so same thing here. Max P, quote unquote, solves this problem by changing the problem. You know, these problems that don't have a solution, people often claim they have a solution, but they don't really have a solution. They change the definition of the problem, and so then they solve a different problem. And the way we do this with max P is we can make, that's why it's called max P, we can make the P, the number of clusters, endogenous, meaning it comes out as a solution. But, you know you can't just do that. So you got to do something to get there. And what we do to get there is we impose a minimum threshold for the cluster size. So the minimum threshold is typically what I call a spatially extensive variable. You know the difference, you should know the difference between spatially extensive correlates with size, spatially intensive does not. So a rate or a density is intensive, total population count, total household count, those are spatially extensive. So think of this in terms of maybe redistricting, and say we want to divvy up, or redistricting is not a good example. A better context is the computation of rates for rare events. Remember the empirical Bayes smoothing. The essence of the problem was that our denominator wasn't large enough. And because it was a small denominator, we had a lot of variance, and so bad precision. So one way to deal with this is to borrow strength. That's the empirical Bayes approach. Another way to deal with this is make your denominator larger. So how are you going to do that? By grouping small units, small areas, into larger areas. And so how large? Well, depends on the agency, but there's NIH and CDC guidelines that basically preclude the reporting of rates if the denominator is not large enough. And what is large? It depends. Sometimes it's 50,000, sometimes it's 100,000, 200,000. So that would be your critical threshold. You would say, okay, I'm looking at these rates of rare events. I have a lot of small areas. They're going to be too imprecise. I'm going to group them. And I'm going to group them so that they are contiguous. They are as similar as possible on a bunch of criteria. And they have at least X number of people in them, or X number of households, or X number of houses. And that is our constraint. And as it turns out, if you do that, you can formulate this as an integer programming problem and find a solution that maximizes the internal similarity, finds the best K, or P as we call it here, and is spatially contiguous. So in some sense, it's the best of all worlds, but it really isn't, because the data dictate the shape of the regions, and contiguity is the key. It's not compact. So this is where we get these kind of stringy regions which meet the minimum population constraint, are contiguous, and are similar internally in terms of the attributes that we choose. So how do we do this? And this is just, if you've never seen this, give you a taste of what operations research is like, or what integer programming is like. So it is basically a constrained optimization problem. So you want to maximize an objective function subject to constraints, right? So classic example, you want to maximize your budget, your food intake. You have a couple of things that you can eat every day. They all cost a certain amount of money. You only have so much money. And then it says you have to eat at least this much of fruits and this much of vegetables. And so these are all constraints. And so how do you maximize your overall food intake subject to these constraints and subject to your money? So classic optimization problem. So here we have to figure out what is it that we're going to maximize and what are the constraints. And what's tricky about this, and the reason I spend a little bit of time going over this, a whole class of spatial optimization problems is decision variables that can take only values of 0 and 1. That's the integer programming problem. So we have some notation, which I always have to look at again, but the key ones is I is an individual unit. So the I will be our departments. The K is basically the K from k-means. That's the, I don't know why it's K, it should be P, but it's really the number of clusters. So K can be, you know, from 1, everything is one cluster, to N, every single observation is its own cluster. So it's in there, and is a decision variable. We will get the maximum K as a result of this process. So then the next is kind of tricky. So the way that Max P deals with contiguity, it starts, of course, with a weights matrix and then figures out for each observation what are the neighbors with a particular order of contiguity. So order of contiguity 1 is 1 step, contiguity 2 is 2 steps, through one that is 1 step, and we've seen that before. So that's the C. Then, and C can go up to Q, that's the maximum, which is n minus 1. Then we have our weights matrix, Wij. We have capital N, which is for each location, the set of areas that are adjacent. So basically that's a row of your weights matrix, but with the zeros taken out, right? Then we have the Dij, which is the same Dij we always have, the dissimilarity. Then we have something really weird, which is, and the reason I want to show you this is one of these tricks that people in operations research use to get particular solutions. So this is a number which will be, to make a long story short, force you to get the best K. So it penalizes to too high a K. So we try to go, as we know, the larger K is, the better our objective will be, but we don't want to go too high, so we will penalize K if it tries to be too large. And then we have our constraint. Li is our spatially extensive variable in each location I, so that would be the population of each department, for example, and then the threshold is it has to be at least 100,000 or it has to be at least 50,000. Okay? And then we have two decision variables. The key one is xkc sub I, and that, you see there's 3 indices there. So for every location I, this is 1 if this area is assigned to region K, where K is one of the clusters, at the order of contiguity C. That's kind of the tricky part. So that's how we enforce the contiguity, is that we only allow one order of contiguity cluster set. And it's a little tricky, so we have these this xkci as the main decision variable, and then tij is, if you wish, the allocation part. So in essence, this is a location allocation part. The xik0 will be the seeds or the cores of the potential cluster. So those are our locations. And then the tijs will be the allocations of each location to one of the sub-areas. So that's, in principle, how it works. So then, how it really works, and this might take you some time to read through, and I just give you a little bit of intuition or some examples of how weird this might seem at first sight, but it works, right? So the objective function, as I said, there's this trickery, and you will want to get a higher K because that gives you a better similarity, which is the second part. So the Dij and Tij, you can Tij as sort of similarity between I and j. So if you sum the Tij multiplied with Dij, then you sum the within cluster similarity, dissimilarity measures. So that's your objective function that you're trying to minimize. And then the first is the trick to get you the optimal k. And so now we take a look at these constraints, and let's see if I can remember them. So let me jump ahead and then I'll backtrack. So the logic of the objective function: the first term controls the number of regions. The second term controls the pairwise dissimilarities. And we, this weird log term is in there to make sure that a solution with a higher value of p will always be preferred over a lower p. That we know that in terms of dissimilarity, the higher the p, the better. But for a given p, we try to get the best solution. And so this avoids mixing p and the clustering thing. So in essence, it does a k-means kind of like thing for different values of k, but internally, I mean, this is maybe a poor way of putting it, but internally it does this creep plot kind of logic, right? If it doesn't improve enough, then you don't increase the p to the next value. You stop. And that's why you give this big penalty to the first term. So then the constraints, let me do it in words first and then I'll revisit. So as I mentioned, there's a location allocation type of logic. So each region starts with a root area. So xi means region I is assigned to the root area 0 for cluster k. So if we have 5, if k is 5, then of all the xi's, 5 of them will be 1, all the other ones will be 0. And then in each region, we can only have one area of contiguity for a given order. That's the weird thing here. That's how we get the contiguity constraint. So that's where the ck or the kc is there. So k0 is the core. k1 will be one that is first order contiguous to the core. k2 will be one that is second order contiguous to the core, and so on. And then obviously the constraint on the minimum size has to be satisfied. So the minimum size is constraint equation 5. That's the easiest one. So, you know, the sum over all the contiguities C for a given k of all the i's that are in k, since these are 0 and 1, there will be 1 if I is in k, and then you multiply it by the population of I. That population has to exceed the threshold. So you kind of mathematical games we're playing with these zeros and ones. So obviously, at the top, we can only have one seed for each cluster. So each of these possible k's, only one of the i's can be 1. And so the sum, and this is typical for integer programming, so this seems really unwieldy, but it's really very simple. All it says is each cluster can only have one seed. And so how do we mathematically do that? If we sum all the values of x for each I, x for a given k, 0. So for cluster number 1, how many k zeros can we have that are not 0? Each cluster has one seed. So if you look at all the xi k0 for a given k, and xi kc, which is 0 in this case, can only be 0 or 1, there's only one of those that meets the criterion, right? So you pick location 25 to be the seed for cluster number 1, x25 k0 is 1, and x for all the other i's, k0 is 0. So the sum, this is why it seems unwieldy, but it's really very simple. All that this equation 2 says is that there's only one core in each cluster, because xi k0 can be either 0 or 1, and if you sum it over all the possible observations, there's only one of those that can be 1. So the sum over all the I of this decision variable has to be less or equal to 1. Okay, that's how you have to start to think. And so I'll leave it up to you to figure out the other ones. The most complicated one, in my view, is number 4. And number 4 is complicated because it gets these contiguity orders in there, the C and the C minus 1. So that one basically, if you look at it hard and you put in zeros and ones, you see that it forces a string of contiguities. So as you add a new element to the cluster, it has to be contiguous to a previous one that is already in the cluster. And that's, so all of this, and then of course, x, the decision variable, is either 0 or 1. And that's why it's called an integer programming problem. So then we, how do we solve this? It's technically mixed integer programming because there's some continuous variables in there as well. But all the heuristics work in basically the same way. So all these problems are search problems, right? You have combinatorially, I forgot the number, but so even in our simple example, the number of possible combinations is larger than the number of seconds since the start of the universe. So that gives you an idea of how big a problem this is. There is no way you're going to enumerate them and then pick the best one. You just can't, right? So you have to be smart. And so you start with what we call a construction phase, is where you get a set of feasible solutions. For example, my eyeball solution would be a feasible solution. That is how you start. And then you have a search process, which is local in the sense that for each of these clusters at the edge, you see if you can swap and improve the value of the objective. And so there are a bunch of different ways in which you can do this. You can use fancy stuff like simulated annealing or taboo search. Basically, those methods try to keep you from getting trapped into a local optimum. So you can think of the optimization process, think of it as hill climbing, right? So you get on the slope of the hill and you want to get as high as possible, you keep climbing up. You reach the top of the hill, you stop. Now what if there's another hill that's even higher? Well, you won't ever get there because it tells you I'm on top of the hill, I'm done, right? So a smart algorithm will actually, as you climb on the hill, will kind of bump you off a little bit and maybe bump you off enough that you get from this hill onto the other hill of the bigger mountain. And it keeps you from getting trapped in these local optima. That's the rationale behind it. How you do that mathematically is kind of complicated, but that's the idea. So instead of just straight steep descent, climb up the steepest slope you can find, you actually check out some of the other slopes that might actually give you an even better solution. And then greedy algorithm is just kind of grabbing and moving. It tends to be very fast, but it doesn't necessarily give you a very good solution. So this is what we get. So look at the p equal 4. That looks very sort of similar to what I came up with my eyeball method. It's a long stringy region, and then the other ones are fairly compact. The population threshold determines the p. In the French example, if you set it to 10%, you end up with a p equal 8. If you set it to 20%, you get p equal 4, because it is a hierarchical process. If you get the population too high, then you may not get the k that you want, because you're stuck. in a subtree. So if your subtree only has 5 elements in it, and these 5 elements have a population that sums to less than your threshold, you're stuck. You cannot go further. So this is something to keep in mind. So here's just a quick comparison of all 4 for the 4 case. So there's my eyeball method, which gets exactly the same solution as the max-p. Centroids is fine, but not better than scalar in this example, but that's not always the case, you know, by any means. But what does seem to be the case, at least in my experience, is that max-p, one, it converges, which is an if, you know, gives you better results than scalar. Scalar is very nice, but tends to get stuck in suboptimal solutions because of the hierarchical nature of this. So max-p doesn't have that. It constantly swaps and swaps and swaps and looks for better and better solutions. And it can keep doing that for a while until it gets to a good solution. But anyway, in sum, I've said this before, you know, multiple attributes is complicated. This trade-off is complex. There's no best approach. It really, in some sense, is problem-specific. So in some problems, like a regionalization problem where the compactness is critical, you have to take that into account. In other instances, it may not matter, and then just throw in the x and y in there might be good enough. Is critical. A bit potentially misleading in that if you don't really know how this works, you say, oh, great, you know, click on this, I want 4 regions, here they are, I'm done. Well, you're not, because there are many different ways in which you can do that, and you have to keep in mind what is my objective, what are the constraints, and also in practice, how much time do you have? You know, you can, some of these methods are very slow and take a very long time to converge, so if you're under the gun, that's not very practical. Right? So you have to keep that in mind as well. So I have the lab notes out there. We have, so all this stuff in GeoDa is still very much under development, but everything that's there works for the French data. And that's all I'm going to say.